we are going to continue on our journey with History of the Notes Part 4. Today is Tuesday. Tomorrow we're going to do History of the Adams Notes Part 5, and that's going to be live because that is the hardest lecture of the unit. Most of this stuff probably you don't have any questions. But tomorrow when we have to start filling in orbital charts, it gets very challenging. So what we're going to do is we are going to have you guys call in during your class period to get your participation points, see if there are any questions, and then we're going to teach you how to fill in orbital charts live. So you will need your packet. To start today, you are going to want to find atomic structure bell work number 3. You also need your trusty dusty periodic table. And I say go ahead and pause the program and give yourself about 5 minutes to see if you can't fill in atomic structure bell work number 3. I guess a little bit of a review. Z always tells you number of protons because remember that's your atomic number. A is the atomic mass, which is the combination of protons and neutrons. Remember, the only things that have charge are electrons are negative, protons are positive, and the full atomic symbol is A, Z, charge. And the charge, if you see on this chart here, and I promised you every chart would be a little bit different, so you can't just get used to doing first column and last column, the charge is going to be in the front. So go ahead and pause the program here and see if you can't figure out how to fill in this bell work. All right, so hopefully we did good here. So the first thing you're going to look up beryllium. He has 4 protons, so I put that number here. 9 minus 4 tells me I have 5 neutrons, and apparently this is giving away answers. If I want to be a +2 charge, that means I have +4 here. How many minuses can I have in order to still have a +4 charge? So I need 2 less than that, so that is 2. And then your full atomic symbol would be Be with 9, 4, and then +2. Iodine, you look them up, has 53 protons. And don't just necessarily take the mass off the periodic table. That is correct on this particular one. But what you want to do is you want to do 53 plus 74. That gets you 127 is the mass. If I have 53 pluses, how many minuses do I need to have an extra -1? Well, that would be 53. One more than that is 54. Again, like I said, hopefully you have done all of this, so I'll just give you the rest of these answers here. Also, the key is attached beneath this lecture video if you would like to check. But we already took a quiz on this. Hopefully we're feeling good. You'll probably have another one of these on your quiz, again, on Friday, because this doesn't go anywhere. This is a huge portion of the atomic structure unit. So hopefully you're feeling A-okay with that. Perfect. So then what it wanted to do is it would like to talk to you about Bohr's model of the atom. Remember, Bohr's model of the atom has a nucleus in the center. Okay, we're still going with Rutherford here, saying that's that. But what we have now are these things that they're called orbits. And the orbits are predictable little paths that the electron travels around, just like planets around the sun. And there's low energy on the inside and high energy residing the further out you go. And it says, what element did Bohr best predict the colors of the emission spectrum for? And that element was hydrogen. And the reason why it works so well for hydrogen is so simple. As the elements got bigger and bigger and bigger, we had a little bit of a harder time using Bohr's model accurately. So we're going to move into that. But before we go there, do scientific models tend to become more complex or more simple over time? And that answer from our first lecture, the very beginning, the Monday before Thanksgiving, said more complex because we gather more information. So remember, and the big idea is going to be how the atom evolved over time. So the first thing is Dalton thought that the atom looked just like a marble. No pieces, no parts, no nothing, just a marble. Then Thomson came along and he found the electron and thought it looked like plum pudding. So we have this positive mush, and in the positive mush are the negative electrons. Then Rutherford did the gold foil experiment where he fired a bunch of bullets there and accidentally hit something And what he hit was the nucleus. And he just said, teeny tiny nucleus, most of the atom is empty space. He said the nucleus was three things: small, dense, positively charged. And then yesterday we talked about Bohr, and what Bohr said was there's that small, dense, positively charged nucleus, but electrons travel in these orbits or predictable paths like planets around the sun. So that is a long way more complex than just a marble. Okay, so over time, these things become more complex. We're going to make it even more complex starting today. So if I was you, I would get out. So we're done with this packet for today. Go ahead and get out your notebook. We're going to continue this on. We're in History of the Atoms Notes Part 4, extending Bohr's model into what we're going to call quantum mechanics. So as you're labeling this up, quantum mechanics is our current working model. Like if you were around in Thomson's time, the current working model was the plum pudding. Currently, we're going to take Bohr and we're going to extend him into the model that we are currently using. So I kind of harped on it yesterday. If this gets very confusing, so this is why it's in a chemistry level class. If you understand Bohr as an everyday person, that's great. But we need to extend that a little bit further to understand exactly where electrons are around the nucleus. Okay. So the biggest problem that we had here is by the mid-1920s, when we were trying to work with some spectra of some bigger elements, Bohr's model was not working. Okay. Bohr's model was not all the way correct. And it was great for atoms with a small number of electrons like hydrogen, but as they got bigger, it started to fall apart. And everybody was trying to figure out and tripping over themselves, trying to figure out where these electrons are. What are they doing? I mean, if they aren't in predictable paths, where are these electrons? So what we needed somebody to take a look at the same thing that everybody else was looking at and see something different. So I have a question. What do you see? Usually this is a lot more fun of a lecture because it's involved, but here we go. So there's everybody's looking at the same picture. You might see two different things. Some people see an old woman and some people see a young lady. Let me see. What do you see? Some people see a duck and some people see a rabbit. Is it a duck? Is it a rabbit? Is it both? Which direction is the window opening? In or out? This one is supposed to have three faces. I can get an old man with a big nose. I can get a lady looking away. There's supposed to be like an older woman looking down. I'm not sold on the third face, but you know, if you see it, you see it. What do you see here? Awesome. So there's two different things. You might see kind of an Inca statue looking that way, or it looks like it's like an Eskimo person off to the side, maybe looking. This is their back. These are their feet. This is their arm. Perfect. What do you see? So some people might see a face of a woman with a heavy shadow on it. Some other people might see a guy with a saxophone. Maybe here's like a note. I don't know. I don't know how to draw notes. What do you see? Awesome. So all of us are looking at this. Some people might see the shadow or the outline of a person, or some people might see that it says the word liar on it. So, but what we needed was everybody to look at the same thing and see something different. So what we have is a big question, and I want you to write this down in your notes. Is an electron a particle, or is an electron a wave? Because some of the data they were getting started to support that electrons might be waves of energy instead of particles of energy. And the answer to that question is yes. Okay. And you're like, what? The big part of the note is that an electron is a particle and a wave both at the same time. So a wave, electron is and this is supposed to say particle and also say wave at the exact same time. So it's very hard to wrap your mind around. It is a particle and it's a wave, depending on how you're looking at it, okay? But an electron can be both. So let's talk about the scientist that got us to this understanding. His name is Mr. de Broglie, Louis Victor de Broglie. He was working in the 1920s, and he is the first person to lead us into our new model called quantum mechanics. And what de Broglie said is that electrons can show wave-like properties, and his new model is that you have a positive nucleus, but then you have negative energy, okay? And so no longer are we drawing them as little e's, but they can, because they can be both. So they're either little e's at a certain point in time, or electrons can be all around the nucleus at the same time as a wave of negative energy, okay? So it can be both. So then came along another person, and depending on where you are in your psychology, he's a very smart, very intelligent person that kind of thought outside the box on a lot of stuff. And his name was Erwin Schrödinger. Schrödinger was also trying to figure out where exactly these electrons are and where they are going. And what I would know about Schrödinger is that he developed a complex mathematical equation to try to describe electron motion. So they have been doing experiments, and they had some success with doing some electron scanning, things like that. But they were trying to figure out exactly where an electron is. So I actually took some notes from a quantum mechanics lecture at Georgia Tech University. So you're writing Schrödinger developed a complex mathematical equation to describe electron motion. And let's take a look at his math, shall we? So it starts off here. So to solve Schrödinger's equation, must make an assumption about the wave as a function. And then you go and you carry the one. And then you're going and you have an E equals scribbles. And then you keep going, and then you have your Hamilton operator and your momentum operator. And then you keep going. And this is still one problem here. He's still trying to figure it out. And then it goes and goes and goes. And then general solution coming down to the end here. Still one math problem. What does it mean? Well, when you get to the very end, the conclusion for this is that there are many different possible states that can be obtained or held by an electron with different wavelengths and different energies. So what does all this mean? It means we have no idea where an electron is. Okay, what I would write down underneath him too as well is that we have no idea where an electron is. No idea. For 100%, you can't tell me where an electron is. However, sometimes when you learn you don't know something, you actually learn that helped you figure out what you don't know. So we know that orbits are out. Bohr is wrong. And so now we know we have to modify what we know. Okay. So Schrödinger's big help is that he concluded that there are no predictable paths. All right. So what does that mean? We know. Then another person came along. He is Werner Heisenberg. If you know anything about pop culture, the name probably rings a bell to you. The character from Breaking Bad, the main character, calls himself Heisenberg. A couple people speculate it was written because this young man was extremely intelligent. He did a ton of work in his short life, but he did succumb to cancer and he passed away. So that could be kind of why. And then if you know about his uncertainty principle, that could also be why they called him Heisenberg. So pop culture reference for you. Werner Heisenberg was working in also the 1920s, and he was also trying to figure out where these electrons are. And what he deduced is called the Heisenberg's uncertainty principle. And what that says is, we'll write it down and then we'll talk about it. It is impossible to know both the position and the momentum of an electron at the same time. It is impossible to know both the position, and another way to say position is where, and the momentum, which is speed and direction, of an electron at the same time. It is impossible to know both the position and where it's going. So you can know one or the other. Okay, so think of a picture of a car. So can we know position? Because these electrons are so tiny, they go so fast, all we have best is the idea is to take a picture of it. If you think of a picture of a car, okay, and you know, let's say these are 10 feet apart, so you know that this is about 3 feet away from that, and maybe it's about 7 feet away from here, and you know, then you can tell about how far down it is. You know exactly where this car is, where the car is. Do you know which way the car is going? We think it's going forward because that's how cars usually go, but electrons don't just drive on streets in straight lines. This is something that can move wherever it wants, however it wants. So are we sure that it's going forwards? Maybe it's going backwards. Maybe it's going to shoot up to the sky. Maybe it's going to slide towards you. Maybe it's going to slide away from you. So when you know where it is, you can't know where it's going. But if you can take a different picture of a car, maybe one where you open up the aperture a little bit, you see like a smear of it, you know that the car went from here to here. If you know that each of these blocks are about like 1 foot, and you know how this is like 10 seconds that it was open, you can know how fast it's going. You can know the direction it's going. But can you tell me exactly where that electron is or this car is? No. So in Heisenberg's uncertainty principle, you can know one, but you can't know both. You have to do your best to predict where it's going. So what we're going to do is you're going to have to use probability to figure out where electrons are around the nucleus. So we have to use probability. So that gets us to our last little bit. So if orbits are out, what are we going to call where the electrons are around the nucleus? And that's going to move us into this idea called orbitals. I know it's confusing because we have orbits and orbitals. How are we going to keep them straight? I think they were giving a nod to Bohr, saying you weren't completely wrong because he's still going to be right about the low energy close to the nucleus, high energy further away. So he's going to be a little bit correct on that. But these predictable paths, we don't know where electrons are. We just know where they probably are. And so that's called an orbital. An orbital is a region of space where there is a high probability, where there is a high probability of finding an electron. Region of space where there is a high probability of finding an electron. It's like if I were to say, I'll give you $1 million if you can go find me a bee. You're probably going to look in a beehive. 99% of the time, you are right that there is probably a bee in a beehive. But are you guaranteed to be there? Are you guaranteed you won't walk out that door today and boom, there's a bee? Whoa, what, you're not in a beehive? What are you doing out here? So the idea is that orbitals are regions of space where there is a high probability of finding an electron. Okay? Each orbital can hold 0, 1, or 2 electrons, but no orbital can hold more than 2. And so there's a bunch of different shapes. They've done a lot of math to try to figure out how and why and exactly where. Okay, but this is a very complex idea. So we're actually going to talk about this a little bit more tomorrow when we can do so in person and kind of get some questions answered, things like that. Okay, so orbits are out, predictable paths. What are in are these regions of space where there is a high probability of finding an electron. Okay, all right, thank you guys. We'll see you tomorrow live during your class period.